to VFD Vibes, your place for all things related to variable frequency drives. If you're interested in how to make things turn or manufacturing technology in general, then this is the place for you. I'm your host, Greg Wichman. In a previous episode, we've explored different power system configurations, and today we're going to continue that conversation by looking at something just as critical, grounding and bonding. These terms are thrown around a lot, sometimes interchangeably, but getting them wrong can lead to nuisance trips, drive damage, or worse. To walk us through it, I have a returning guest today, Joe Potabaum, an expert in field applications and troubleshooting, who's here to help us break down what proper grounding and bonding actually looks like, and why cutting corners here is never a good idea. Thanks for being back again, Joe.
Well, thanks, Greg. It's good to be here.
For those that didn't listen to our last episode, would you like to give a little recap on your professional experience?
Oh, sure. I'm Joe Potabaum. I graduated with a Bachelor's of Electrical Engineering from The Ohio State University. I've been involved with AC drives since around 1980, with various companies. I came to Yaskawa in late 2000. I've been here ever since. I started in the design and development of AC drives, and then later got involved with the applications of AC drives, in particular vector drives. And, of course, part of that, applying the drives has to do with connecting them to a power system. And that's how I got involved with really doing a deep dive into the power systems, because they are part of the whole system that runs through the drive to the motor.
Yeah, in the power system episode, we went from transmission through transformer, high voltage, medium, low. Today, we're talking a little bit more local to the drive itself. And let's start by defining a few terms. Can you tell us what the difference is between grounding and bonding?
Well, I think we have to talk about the difference between grounding and grounding to start. In a previous discussion, we talked about power system grounding, and this is commonly referred to as system grounding. What grounding or earthing means is to somehow or another connect something to the earth, literally the planet Earth. And one of the little lies we tell ourselves is that the surface of the Earth is an equal potential surface, meaning that if I were to measure the voltage anywhere on the surface of the Earth with respect to any other point on the surface of the Earth, I would see zero, which of course is not true because Earth has an impedance. But anyway, so we talk about connecting something to the earth. The idea is that someone's standing on the earth, if they were to touch anything connected to the earth electrically, they're not going to get a shock. So that aspect of grounding we refer to as equipment grounding or protective grounding, and bonding is all part of that. What is bonding? Well, bonding is tying wires to the dead metal parts of any piece of equipment. Dead metal parts are things that are not intended to conduct electricity, like cabinet doors, like the walls, the back panels of cabinets, the cases of motors, things like this. These are all parts that are not supposed to have any electrical potential. These all have to get tied together and eventually tied to the surface of the earth or grounded. Now, the term grounding, we even talk about equipment grounding. Grounding and bonding are used synonymously, really, in real life. Like we talk about running a green wire from the cabinet to the grounding bus that's on the back panel and this type of thing. Well, we call it grounding when the code will refer to this as bonding.
So bonding is really just tying different devices or pieces of metal, for that matter, to the ground.
Exactly.
It's just when you talk about grounding, it's maybe a device that is specific to having a ground or needing one, whereas bonding is taking something like a panel door, which we don't want power running through when we touch it.
Right.
And
oftentimes, if you're designing an industrial facility, you will put a network of rods, these will be usually copper-coated steel, under the building. This will form what they call a grounding grid. And there will be taps brought up from this grounding grid on the pillars of the building, and every so often these taps will be connected. These will be the true grounding taps. you don't have to connect every piece of equipment right to that grounding tap. They can be tied to another piece of equipment, which is in fact tied to the grounding tap. That's where the term bonding comes in. Strictly speaking, the only wire that's really grounded is the one that is tied to that grounding grid that's under the building. Everything else is bonded to that grounding wire. Now, why they make the distinction is up to the purists.
Yes.
But essentially, anything that's bonded is essentially at zero potential, and it's basically for protecting people. And it has to be sized appropriately so there actually is a ground fault. We have a large enough wire that can carry that ground fault current long enough for protective devices to open, fuse to open, or a circuit breaker to trip, in other words, break the circuit, something that can interrupt this ground fault. So that's protective grounding. That's bonding and protective grounding. And system grounding, which we talked about before, is some part of the power system that is feeding the drive has to be grounded. This is most commonly the neutral. As we discussed in the previous podcast, most 480-volt industrial three-phase systems are connected as a Y configuration with that neutral solidly connected to ground. Okay, and that ground is called system grounding. And yes, eventually the system ground finds its way to the protective ground. It's all the same thing. But all these protective bonding and grounding wires are not intended to carry current unless there's a fault.
So the system ground can determine how the system actually operates and the different voltages across line to line.
It's just how the power system is referenced to the earth. The equipment ground is there to protect people who might come in contact with the equipment.
Perfect. That makes sense. Let's bring it over to what we like to talk about, VFDs. What are some of the key best practices when we talk about grounding a VFD properly?
Well, look in the manual, see how it tells you to ground the VFD, and follow the instructions.
Read the manual.
Yeah, read the manual. The Yaskawa drives have usually two ground connections. One is intended to go to the back panel, to go to the main bonding terminal within the enclosure. Most drives are in some kind of equipment enclosure. And then it has another contact, another terminal, which is intended to go out to the motor, to be the ground wire for the motor. And that's just to assure that the motor case is eventually grounded somewhere back in the drive cabinet. And the reason that's important, a motor, as a practical matter, the motor case is going to be bolted down to something, and that something is usually connected to the frame of the building. And so the motor case is going to be grounded most of the time all on its own, except when it's not. When the motor's manufactured, they paint it. And they paint the feet, right?
Yep.
So there's a possibility to tighten the screws down on the feet and you don't have a very good ground connection. That's why for a motor it's always required, there's a little grounding screw up in the conduit box of the motor where it's intended to have a ground wire physically connected there. And that ground wire is brought back to the cabinet, the drive, to ensure that the motor and the cabinet are all at the same potential.
I have heard, I feel like for VFD installations, this idea of scraping paint off of a back panel and things like that.
Yeah. Now, when Yaskawa builds panels, which we do in Oak Creek and now will be over in Franklin, when we build panels, we actually have a screw that is the intended place for all these grounds to come together. Grounds, I should say bond.
Yeah.
The bond, if I use proper terminology. Everybody calls them ground wires, but yeah, the green wires all go back to that screw.
So you mentioned grounding the motor to the drive. What are some of the best ways to do it? I know you can run wires in a conduit. There's these shielded VFD cables. What are your thoughts around these?
Well, I might want to interject one thing here, and that the ground terminals on the drive are not connected to any of the electrical circuits of the drive. They are connected to the case of the drive and the heat sink. Okay. They're really there so that if there is a fault within the drive, that fault current goes somewhere other than to electrify the case where somebody might get...
Could touch it. It drives it to ground so our circuit protection can once again
And in fact, one of the tests done in the manufacturing of the drive is to actually put a very high voltage between the drive circuitry and the ground on the drive to make sure the drive doesn't have a breakdown within the drive.
Okay.
So they'll put several thousand volts there just to make sure that the drive can withstand this. So this ground is really, truly a protective ground. It's got nothing to do with the drive circuitry.
Gotcha. So when we talk about connecting the drive to the motor, though, and again, there's discussions around shielded cable, VFD cable. What are your thoughts on those?
Well, I usually recommend that customers run 4 wires out to the motor, 3 conductors for the 3 phases from the drive, and a ground wire, an insulated ground wire, through a plain old steel conduit, which is tied to the cabinet and tied into the motor, and that's it. Okay, that's sufficient to protect the conductors. And why would you shield the ground wire? Well, typically steel conduit is made out of galvanized steel, which has a zinc coating. If you have a bare copper wire in there, now you have a copper zinc situation where if you get moisture in there, it'll form a battery and corrode the conduit. So you want to insulate that ground wire so you don't have the potential for electrolytic corrosion.
And running the conductors in a conduit like that, that will protect other devices from any EMF
yes.
or noise
because,
that could be coming from those.
Well, the drive uses a pulse width modulation to create what we say create the voltages that power the motor, but actually the pulse width modulation is designed in such a way that it drives 3 sinusoidal currents into the motor. Okay, yes, the voltages come out to be, there is an equivalent voltage associated with this pulse width modulation, but really, strictly speaking, it's designed to create sinusoidal currents in the motor. However, a byproduct of this switching is that the carrier frequency is there is a common mode component that drives any capacitance that's between the motor windings and the motor case or between the motor leads and whatever's around them, the conduit. And this capacitively coupled current at the carrier frequency has to make its way back into the drive. Now, the less capacitance you got, the less capacitively coupled current you have. Putting 3 wires in a conduit with all the space that you have to leave in there generally means you have a minimal amount of capacitance. If you put those 3 wires and wrap a shield around them, now you have considerably more capacitance because the wires are held tightly together and the shield is held tightly around the wires. So there will now be more current flowing, high frequency current flowing in that shield. And that, of course, goes back to the drive cabinet. Could this be a problem? Well, sometimes. But on the other hand, it does shield those conductors from anything else that might be near them.
So if you're running a lot of cables in a wireway,
In a wireway, this makes a certain amount of sense. What does not make sense usually is to run this shielded cable inside a conduit. I would recommend that the place where the shielded cables work well is in cable trays where you got many, many motors out there and all their wires are laying in a cable tray. Well, yeah, you want to keep them bundled together so you don't get some kind of inductive interaction between all these wires. And having these shielded cables is really nice for something like that when you cannot run wire in a conduit. However, you have to pay the price with the increased capacitance that you have to deal with and with the increased noise that that's going to produce in other parts of the system.
Now, even with that increased noise and current from it, if you have a very well grounded and bonded system, that should take care of it, where that could be more of an issue when you don't have a well.
Except that what the code requires for grounding and bonding is just a piece of plain old round wire, which is not a very good RF high-frequency ground. In other words, if you really want to do grounding for high frequency, you pretty much have to use copper braid. Okay. And that's that. Some installations do this and do that for that purpose. It's expensive, though, and not really required for the protective grounding, which only requires a round, plain old piece of wire, right? Yep. And so there are a lot of things that are done for EMI and RFI shielding, and they involve using things like copper braid. But yeah, I prefer, in most cases, for most industrial applications, I think your very much ahead to stay simple. 4 wires in the conduit, one of them being the ground, 3 conductors, and it's probably the least expensive way to hook things up.
And get the most benefit that you're looking to get.
Right.
Because where the shielded cable, like you said, might solve one problem, might introduce another problem. I will say cable management is not always where it needs to be, and it's very crazy how many times I've seen a VFD cable next to a network cable.
Well, and I think if you're in a situation where electromagnetic interference, EMI, is a real problem, then you have to design your entire power distribution system around reducing EMI. You can't go in later and say, well, you know what, let's throw a filter at it, let's throw this at it, let's throw that at it and see if it goes away. You have to start at the beginning and say, you know what, EMI is going to be a problem here. For instance, you're in a hospital, you got medical equipment, right? And so you start right from the get-go designing your whole power distribution system around the fact that you have to accommodate heart monitors and everything else along with the air conditioning system. So you start from the ground up building your system so that you're dealing with these things, with EMI, with harmonics, with whatever. Because it's really expensive to come along later and say, hey, you know what? We got too much EMI or we got too many harmonics. So the good thing is to know you're going to have to deal with these early on. And frankly, the reason that solidly grounded 3-phase systems, the typical Y connection with a solid ground, is also a pretty good way to deal with EMI in the system. So
I've worked with vendors that want to get that message out to people from the get-go. We're talking IT cable and cable management companies that specifically talk about your typical grounding system is not always sufficient in a lot of these new applications and installations, and they talk exactly what you're saying. I feel like I've even heard to the point of having 2 separate systems. That might be overkill, but at least using the proper connections, like braided as opposed to a round copper.
Well, there are a lot of things that you could do if you're at the specification level. But as a practical matter, the specifications are written by consulting engineering firms who cut and paste from the previous specification, right? I mean, that's the fact of life. And so they walk away from it, and then you have to deal with this later. And of course, we have ways of dealing with it. We sell little EMI filters. We have drives with EMI filters built in that you can engage. They're designed to deal with these kind of things.
Because very often do we get to start with a blank slate and
build
it properly.
Right.
So another term I've heard is a ground loop. And would that ever pertain to a VFD installation?
It can. Usually ground loops have to do with the control systems. And the term ground is often used for the most negative potential. Like we have some kind of PLC or PLC interface that's working on 24 volts. Well, they'll say the negative side of that 24 volts, they'll call it ground. Now, whether or not it's actually connected to ground somewhere. And when they talk about ground loops, we're usually talking about a control system where, for instance, on the drive, you have a 24 volt ground for all of the inputs, and you got, say, 2 PLCs or whatever. Maybe you got multiple drives connected to the PLC, and you run out to that 24 volts. And, oh, by the way, that also goes up to the encoder, which now goes over to here and down to there. And, oh, by the way, now we got a big old ground loop, right? And the problem with the ground loop is that if I want to make an antenna, one of the ways to make an antenna is to make a loop. Like on these AM radios, which you used to have in the back of the AM radio was a bunch of wires wrapped around in a loop, okay? So if I want to pick up a signal from anywhere, like random EMI floating around within a facility, I can do that real nicely by creating a loop. Well, if I have signal conductors, I don't want any stray voltages on these signal conductors that could be interpreted as a signal. So one of the ways of avoiding that is to avoid loops in any part of the signal circuit. And oh, by the way, the signal circuit goes out and it comes back. It goes out through one lead and comes back through what we might call the ground or the return.
Yep.
So if that's formed a big loop with things, it'll pick up all kinds of noise and everything else.
So you're creating large antennas within your facility basically because of these interconnected grounds.
Well, a loop antenna is designed to pick up the there's the magnetic portion. An electromagnetic field has two components, the electrical component and the magnetic component. And the loop antenna is designed to pick up the magnetic component, whereas a wire antenna, just a piece of wire up in the air, is designed to pick up the electrical component. And most of the components of noise in any kind of industrial facility are definitely magnetic. They're caused by currents flowing through wires. Because you might have 480 volts of voltage, but you might have thousands of amps of current. And let's say you take a large motor, a 100 horsepower motor is rated around 124 amps. That's within in the code book. And so I'm putting 124 amps out and it's coming back. That is a lot of amps going through a piece of wire that could be easily picked up by a loop that's nearby that circuit. Now, theoretically, I got 3 phases going out there, so anything that goes out wire A comes back through B and C. So the stray 100, that 100 amps isn't generating a stray field, except that current we talked about before that's flowing through that's capacitively coupled from the motor winding to the motor case. Now that is making a big loop that's formed by the output of the drive through the wires to the motor windings, from the motor winding to the motor case, back from the motor case, flowing through all the building. Some of it goes back through the green wire from the motor, okay, a lot of it, but a lot of it leaks out and goes through the building framework to get back to the drive cabinet. So we have these high-frequency currents that are flowing through everything in the building. The last thing we want to do is throw a loop out there in the control circuit to pick this up.
Are there warning signs? What things might start occurring in my facility that might cue me in that I have this problem going on?
Well, if something turns on when it's supposed to be off is the worst case. Believe it or not, you can have enough, and I actually saw this happen, so it does happen, where somebody had a 120 volt coil relay get pulled in by currents induced from a whole bunch of control wires running together in a steel conduit.
Wow, an actual relay pulled in.
An actual relay got pulled in. Okay, and if I hadn't seen it, I would have, it's like, nah, that can't happen. But so there is, these parasitic inductances and parasitic capacitances can be real.
If you suspect this is going on, what are some ways to troubleshoot it? Where do you start your investigation?
Well, that's a big problem. I'd say that tracing down EMI and electromagnetic and noise problems probably accounts for more field time on the part of me and people like me that have gone out to the field than any of these other issues, because they are very troublesome. Because if you're facing a panel, you've got wires and wireways, and they're all pasted in there together, and it's really hard to tell what goes where. And generally, troubleshooting an EMI problem usually involves having to pick apart and find out where wire 103 goes. You got all these red wires with little wire tags on them, and they're going everywhere. They're running all through the cabinet, and hopefully they're separated from the power leads and that. And oftentimes, I'd say many times, where we never did really find the root cause of the problem. Now, oftentimes you trace it back to something, but even if you trace it back, it's something you cannot correct. We've had issues where, for instance, an EMI filter. A customer buys a drive, and he figures he's going to have an EMI situation, electromagnetic interference situation, so he buys an EMI filter that is between the drive and the power supply that feeds the drive. So you come in with your 3-phase windings from out of the circuit breaker, you go into the EMI filter, come out of the EMI filter, go into the input of the drive, and that EMI filter is a big screw on the side that has to get connected to the back plane or ground. They say this is the grounding screws. Inside the EMI filter, there is a capacitor to ground. There's capacitance to ground. That capacitance is there to bleed off the high-frequency signals. Well, it doesn't actually go to ground. It goes to the back panel of the cabinet. I had a situation where, there was a lot of EMI that was trashing the PLC that was also in the cabinet, and the cure for that was to remove the EMI filter, because all the EMI filter was doing was capacitively coupling the noise that was on the input to the drive right back into the back plane of the panel. So we had, got to take that filter out, or at least bypass it. Well, the spec called for a filter, so you had to leave the filter attached to the back panel, but it couldn't be connected to anything, or that would bring the noise right into the back panel. So, yeah, every once in a while you run into something that's strange.
Well, that's what's funny about specs is they often are written for one particular device. You know, the spec says the drive needs a filter or whatever. It's not taking into account what else is in the panel, how things are grounded and bonded in the panel. It's not even taking into account the power system configuration
Well,
that
exactly.
we've talked about.
Specs are intended to give you boxes to check. Okay, so once you're done checking all the boxes, you should be done with the job, right? Except that, no, that's often not the case. You can check all the boxes and still have work to do. And if the box calls for an EMI filter, well, because the guy say, okay, I got a drive, it's going to create electromagnetic interference, well, then I got to buy a filter to put in the front. That should get rid of all of it without really any consideration to how physically the filter is put together. Now, let me say this. That was one instance out of like thousands of installations that have drives. Most of the time, you put an EMI filter in there and it does exactly what it's supposed to do, right?
Yes.
It helps out with the EMI. And the unfortunate aspect of my job and of people in tech support is people don't call tech support and they don't call applications when everything's working correctly. The only time we get a call is when things are not working the way they're supposed to. Now, hopefully that's tech support. Our job, applications, is supposed to be before the sales. We're supposed to tell the customer what to buy and what you need and what's going to give you the best shot of having your particular machine work. Okay, that applications, I think we define it as we solve customer problems with products we make. That's the job of the application engineer. It's not to re-engineer the customer's system or go in there and tell him how to rebuild his power system. That's not really part of our thing. So in most cases, the applications, these drives, are very straightforward. You apply power to the front, you ground everything appropriately according to code, you bring your wires out to the motor, you hook the motor up, you run through your normal setup, motor takes off and runs, and everything is fine.
And I'll just say, so if this conversation is confusing or scary to you, that's exactly why we have our applications team here. You can always call up when you're looking at your purchase, you're looking at your spec, you're looking at your facility, and we have people like Joe that can walk you through ahead of time.
That's a key thing. We can be very helpful as application engineers when you're on the front end. When we're on the back end, and again, we deal a lot with retrofits. So there's a lot of the business of drives is in retrofitting things where we have to deal with a system that is already in place. Okay, that's a big part of it. However, we're better off if we have a fresh look from the beginning. We can be much more helpful.
As we've said, so much easier to design from a blank slate, but
it is.
Usually we're putting a round peg in a square hole, and
exactly.
We have to make it work properly and be safe and up to code and everything else. If someone were installing a drive tomorrow, from all this discussion, what would be your key takeaways or the most important things you'd want them to think about?
Well, the first thing is to know what kind of power supply you have. What does your power distribution system look like? You're going to put this drive, you're going to hook it up to a 3-phase power line. It's very helpful for you and for us to know, well, is that grounded back at the service entrance? If it's not grounded, is there a reason that it's not grounded? It could be that it's supposed to be grounded, it just simply isn't. If you know what kind of power system you're connected to, then we can give you much better advice. The drive may work just fine. Hook it to the motor and be done. If you find out that your power system has a severe amount of imbalance, say more than 2%, we might recommend that you use a line reactor. Now, line reactors are a good bet anyway. I mean, they tend to reduce the harmonics provided by the drive current. They tend to shield the line from stuff the drive might do, and they tend to shield the drive from stuff the line might do.
Yeah, they actually lower the harmonic content coming back from the drive as well.
It protects both ways. There are a lot of customers out there, as soon as they buy a drive, they put a 3% line reactor in front regardless.
Is there any downside to putting in that line reactor?
Nothing significant. Yes, it's going to drop the voltage a little bit, but it'll help out issues like line imbalance. One of the things, we put all these service conditions in the manual. Is, well, our drive will run with a 2% imbalance. It'll run at full load. It'll run We have all these things we say, and by the way, you can be at 40 degrees Celsius while all this is going on. Yeah, that is true. But if you want to run that drive for 20 years, if you want to extend the life, you don't want to do all those things at the same time. And anything you can do, and especially if you're going to push things a little bit in one direction, you want to kind of push back. You don't want to say, well, okay, I'm going to run this drive at 50 degrees C ambient out in the sun. And you say, well, yeah, but if you're going to do that, don't have a horrible amount of line imbalance to put stress on the input rectifiers and the bus capacitors. So if you're going to run at a high temperature, maybe you want to put that line reactor in there. So there's things like that. If you don't do everything all at once, you can usually extend the life. We have drives out there that have been out since every once in a while you call about somebody's got a G3 that's still in service somewhere. It's been there since 1989. These things can last an incredibly long time if they're in.
I've seen some of our customers post on social media like LinkedIn. Every once in a while they open a cabinet up and there's these old G3s, GPDs even from the Magnatech days. And it was really cool to see those things.
Yeah, the equipment is well designed and it's very reliable. But you want to give it every chance, and why put it under undue stress? So line reactors tend to help with the harmonics thrown back on the line, harmonic currents from the drive, but they also tend to protect the drive from line imbalance and from noise that might be on the incoming line. The only exception to that would be a drive like the U1000. The U1000 is a special thing. It's a direct AC to AC converter. Those are a little bit special in terms of what you do on the front end. But if you're talking about like a standard drive, like a GA800.
Standard 6-pulse drive.
Standard 6-pulse rectifier front end, GA800, GA500, FP600. Drives like this, line reactors help a lot.
Other than the user manual, which we've already said, read the manual, are there any other resources that are a good place for someone if they want to learn more about these topics?
Well, you can listen to this podcast.
Well,
but yeah, we have the Yaskawa publishes a whole series of application notes that are available on the website.
That's through our Solution Center, correct?
Right. Although, as an employee of the company, I haven't gone out looking for these recently, so I'm not the one to say how easily they are to find out on our website.
I know they've done some upgrades recently, and I know you can check boxes whether you want, like, I think solutions, maybe applications, and I believe they're going to be implementing some AI into the system soon, too. So for you listeners out there, go check it out. There's a wealth of knowledge.
My experience has been that our drive salespeople, our distributors, are very knowledgeable in the product. What we call regional drive specialists.
Yep.
You guys are incredible, and they have the fast switch back to us. If I get a call from a regional drive specialist, I'm paying attention.
Yep.
Right?
So you've got local regional drive specialists employed by Yaskawa, and then you have our distribution network and all of our partners, which are fantastic resources.
We have a very good training program here, and in order to become a drives distributor, you have to have a drive specialist there in-house, and these guys have to be trained here. So they come here and they get trained by our training department on the real product. And the training classes here are excellent. I mean, I've been through some of the training classes. You say, well, wait a minute, you know everything, right? Why would you go to a training class? And the point is that these guys are experts in making these concepts involved in the drive, making that accessible to people that, most of the people that take these training classes, they don't have engineering degrees. And yet somebody's explaining how an integrator works to somebody who's never seen a calculus class. So the training classes here are very, very good. So the distributors have someone that's been trained here at the factory. If they can't answer the question, they can bump it up to our regional drive specialist. If they don't have a ready answer available, they can bump it back to tech support or to the applications group. In fact, we work a lot with the regional drive specialist.
And you bring up a great point, another resource, because our training is available to our customers as well.
Oh, yeah.
A couple of episodes ago, I actually interviewed the manager of that department, so there is a great episode out there if you want to learn more, because we have everything from in-person at factory training to e-learning, virtual, a whole plethora of training that, again, if you want to do wiring and install all the way through application.
I think you can understand certain aspects of the drive, but not really understand all aspects. And today, in order to actually work with a variable frequency drive, well, you're talking about power systems and things, which, fine, you're talking about control systems. You got to control whatever machine, so you're dealing with that. But you're also dealing with communications. I want to talk to that thing with Ethernet, right? What do I need?
Yep.
And so the range of expertise now that you need in order to deal with these things is more than what most people would have commonly stuffed in their heads. So we all can benefit from going to these training classes.
Absolutely. That's a wrap on today's deep dive into grounding and bonding, something that might not always get the spotlight, but absolutely deserves it. As we've heard, getting these details right isn't just about checking boxes for safety codes. It's about protecting your equipment, preventing EMI and nuisance trips, and making sure your VFD system performs the way it's supposed to. A big thanks again to Joe Potabom for breaking down these concepts and sharing some real-world advice and stories that every installer and engineer should hear. If you've enjoyed today's episode, please like or follow this podcast to stay informed when new episodes launch. And if we're doing a great job, please leave us a 5-star review. Thanks for joining us, and as always, we'll see you next time on VFD Vibes.